Welcome to Dreamy Facts. As the day gently recedes, we invite you to settle into a space of calm contemplation. Tonight, we embark on a journey through the vast and wondrous expanse of our solar system, exploring approximately 100 fascinating facts that reveal intricate patterns, subtle wisdom, and profound beauty within the celestial mechanics that govern our cosmic home. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or retention. We will observe the intricate dance of planets around our star, the subtle adaptations of celestial bodies shaped by immense forces, and the quiet wisdom embedded in the very fabric of space and time. Each fact is a small window into the vast and interconnected tapestry of our solar system, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. We journey from the fiery heart of our sun to the icy reaches of the outer system, understanding how each component plays its part in the grand cosmic ballet. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations, and we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. We begin our journey at the very center of our cosmic neighborhood, with the magnificent star that gives us light and life, and then move outward to explore the rocky worlds that huddle closest to its warmth. Allow your mind to envision these celestial bodies, each a world unto itself, yet all bound together by the sun's immense gravitational embrace. The sun, our star. At the heart of our solar system burns the sun, a yellow dwarf star that accounts for approximately 99.86% of the total mass of the entire solar system. Its immense gravitational pull holds all the planets, asteroids and comets in their orbits, orchestrating the grand celestial dance. Research shows the sun is primarily composed of hydrogen, about 73% by mass, and helium, about 25% by mass, with trace amounts of heavier elements. The energy that radiates from the sun is produced through nuclear fusion, where hydrogen atoms fuse to form helium in its core, releasing an astonishing amount of energy in the process. This process converts about 4 million tons of matter into energy every second. Scientists have observed that the sun is currently about 4.6 billion years old and is in the middle of its main sequence stage, meaning it is stably fusing hydrogen into helium. It is expected to continue doing so for another 5 billion years. The sun's surface temperature, known as the photosphere, is approximately 5,500 degrees Celsius, 9,940 degrees Fahrenheit, while its core can reach temperatures of 15 million degrees Celsius. This constant outpouring of energy is what makes life on Earth possible. Mercury, the swift messenger. Mercury, the innermost planet, is a world of extremes, orbiting the sun faster than any other planet, completing a revolution in just 88 Earth days. Its proximity to the sun means it experiences dramatic temperature swings. Current understanding suggests that during its day, surface temperatures can soar to about 430 degrees Celsius, 800 degrees Fahrenheit, hot enough to melt lead. However, during its long night, temperatures can plummet to approximately minus 180 degrees Celsius, minus 290 degrees Fahrenheit, due to its lack of a significant atmosphere to trap heat. Scientists have observed that Mercury's surface is heavily cratered, resembling Earth's moon, a testament to intense bombardment early in its history. Despite its small size, Mercury possesses a surprisingly strong magnetic field, which researchers believe is generated by a liquid iron core, similar to Earth's. Evidence indicates that Mercury also harbours water ice in permanently shadowed craters at its poles, a remarkable discovery given its scorching daytime temperatures. Venus, Earth's fiery twin. Often referred to as Earth's quote zero, due to its similar size and mass, Venus is a world of stark contrast, shrouded in a dense toxic atmosphere. This atmosphere, composed primarily of carbon dioxide with thick clouds of sulfuric acid, traps heat through a runaway greenhouse effect, making Venus the hottest planet in our solar system. Surface temperatures consistently reach around 462 degrees Celsius, 864 degrees Fahrenheit, even hotter than Mercury. Studies indicate that the atmospheric pressure on Venus is crushing, more than 90 times that of Earth's at sea level, equivalent to the pressure found nearly a kilometre deep in Earth's oceans. Uniquely, Venus rotates very slowly on its axis, and in the opposite direction to most other planets, meaning the Sun rises in the west and sets in the east. A single Venusian day is longer than its year, taking about 243 Earth days to rotate once, while orbiting the Sun in about 225 Earth days. Its surface features vast plains, volcanic structures, and impact craters, all hidden beneath its perpetual cloud cover. Earth, the blue marble, our home planet, Earth, stands as a unique oasis in the solar system, distinguished by its abundant liquid water, a breathable atmosphere, and the presence of life. Research shows that Earth's atmosphere, primarily nitrogen and oxygen, acts as a protective shield, absorbing harmful ultraviolet radiation and maintaining stable surface temperatures. The presence of a strong magnetic field, generated by the convection of molten iron in its outer core, further protects life by deflecting harmful solar winds. Earth is the only known planet to have active plate tectonics, a process that constantly reshapes its surface, creates mountains, and contributes to the carbon cycle, regulating global temperatures over geological timescales. The vast oceans, covering about 71% of its surface, play a crucial role in regulating climate and supporting an immense diversity of life. Current understanding suggests Earth formed approximately 4.54 billion years ago, and its unique conditions allowed for the gradual emergence and evolution of complex biological systems. The Moon, Earth's constant companion. Earth's moon is a familiar sight in our night sky, a solitary natural satellite that has profoundly influenced our planet. The prevailing scientific theory, known as the giant impact hypothesis, suggests the moon formed from the debris ejected into orbit after a Mars-sized body collided with early Earth about 4.5 billion years ago. Scientists have observed that the moon is tidally locked with Earth, meaning the same side of the moon always faces our planet. This phenomenon is a result of gravitational forces slowing the moon's rotation over billions of years. The moon's surface is characterized by dark volcanic plains, known as maria, and bright, heavily cratered highlands. Its gravitational pull is the primary cause of ocean tides on Earth, influencing marine ecosystems and coastal environments. Although often perceived as dry, evidence from lunar missions indicates the presence of water ice in permanently shadowed craters at the lunar poles, offering potential resources for future space exploration. Mars. The Red Planet. Mars, often called the Red Planet due to the iron oxide prevalent on its surface, has captivated humanity for centuries. Scientists have observed polar ice caps on Mars, which are composed of both water ice and frozen carbon dioxide, expanding and contracting with the Martian seasons. While Mars today is cold and dry with a thin atmosphere, geological evidence strongly suggests that it once had liquid water flowing across its surface, potentially supporting ancient microbial life. Features such as ancient riverbeds, deltas, and mineral deposits that form in the presence of water have been identified by robotic missions. Mars has two small, irregularly shaped moons, Phobos and Deimos, which are believed by some researchers to be captured asteroids rather than formed alongside the planet. The tallest volcano in the solar system, Olympus Mons, a shield volcano, is located on Mars, towering approximately 21 kilometers, 13 miles, high and spanning 600 kilometers, 370 miles across its base, a testament to past geological activity. The asteroid belt, a cosmic debris field. Between the orbits of Mars and Jupiter lies the asteroid belt, a vast region populated by countless irregularly shaped rocky bodies, ranging in size from dust grains to dwarf planets. Current understanding suggests the asteroid belt is a remnant from the early solar system, material that failed to coalesce into a planet due to the strong gravitational influence of Jupiter. The total mass of the asteroid belt is estimated to be only about 4% of the Moon's mass, with half of that mass contained within the four largest objects: Ceres, Vesta, Pallas, and Hygeia. Ceres, the largest object in the belt, is classified as a dwarf planet, being spherical and possessing sufficient mass for its own gravity to make it round. Research indicates that asteroids are composed of various materials, including rock, metal, and sometimes ice, reflecting their diverse origins and evolutionary paths. These remnants provide valuable clues about the conditions and building blocks present during the formation of our solar system. The formation of the solar system, from dust to worlds. The prevailing scientific theory for the formation of our solar system is the nebula hypothesis, which posits that approximately 4.6 billion years ago, it began as a giant rotating cloud of gas and dust known as the solar nebula. Gravitational forces caused this nebula to collapse inward, spinning faster and flattening into a disk. The central part of this disk became increasingly dense and hot, eventually forming the Sun through nuclear fusion. In the cooler outer regions of the disk, dust grains and ice particles began to collide and stick together, a process called accretion. Over millions of years, these small particles grew into planetesimals, which then continued to collide and merge, gradually forming the planets we observe today. The inner, hotter regions of the disk favoured the formation of rocky terrestrial planets, while the outer, colder regions allowed for the accumulation of vast amounts of ice and gas, leading to the formation of the gas giants. This process of gravitational collapse and accretion is supported by observations of other star systems in various stages of formation. As we conclude this first chapter, we have journeyed from the luminous heart of our solar system, the Sun, to the rocky, dynamic worlds of the inner planets and the ancient remnants of the asteroid belt. Each celestial body, shaped by immense forces and billions of years of cosmic evolution, offers a glimpse into the incredible diversity and interconnectedness of our immediate cosmic neighbourhood. We observe the foundational elements that set the stage for the rest of our solar system's wonders, preparing us for the vastness yet to be explored as we gently drift further from the Sun's warm embrace, leaving behind the rocky worlds that huddle closest. We feel the true immensity of our cosmic home begin to unfold. The intricate dance of planets, which began with the fiery heart of our star and the formation of the inner worlds, now guides us into a realm of giants, a domain where gas and ice reign supreme and where distances stretch beyond easy comprehension. This next leg of our journey invites a deeper sense of peaceful curiosity, allowing our thoughts to expand with the scale of the cosmos, finding stillness in its vastness. The gas giants, colossal worlds of swirling clouds. Our celestial voyage now carries us to the heart of the outer solar system, to the magnificent realm of the gas giants. These colossal worlds, entirely different in composition and character from their terrestrial siblings, represent a significant portion of our system's mass and hold secrets to its early, tumultuous history. They are worlds of swirling atmospheres, powerful storms, and intricate moon systems, each a universe unto itself. Jupiter, the king of planets. Our first stop is Jupiter, the undisputed monarch of our solar system, a true colossus that dwarfs all other planets combined. We observe its majestic striped atmosphere, a mesmerizing tapestry of swirling clouds, vibrant hues of orange, brown, white, and yellow, painted by the complex interplay of ammonia, hydrogen sulfide, and water crystals, all driven by intense winds. Jupiter is a world of perpetual motion, a testament to the powerful forces at play within its deep, gaseous layers. This mighty planet is primarily composed of hydrogen and helium, much like a star, though it never accumulated enough mass to ignite nuclear fusion. Its sheer size is staggering. It could hold more than 1,300 Earths within its volume. Jupiter rotates incredibly fast, completing a day in just under 10 Earth hours, which contributes to its distinct flattened poles and bulging equator. This rapid spin also fuels the incredible atmospheric phenomena we witness, including the most iconic feature, the Great Red Spot. This colossal persistent storm larger than Earth itself has been observed for centuries, a swirling anticyclone that churns endlessly, a timeless vortex in Jupiter's turbulent sky. Scientists continue to study its dynamics, seeking to understand the enduring power of this atmospheric marvel. Beneath its colourful cloud tops, Jupiter is thought to have a core of dense, rocky material surrounded by a layer of metallic hydrogen, a state of matter so extreme it conducts electricity. This metallic hydrogen layer, combined with Jupiter's rapid rotation, generates an immensely powerful magnetic field, the strongest of any planet in our solar system, extending millions of miles into space and creating intense radiation belts around the planet. Jupiter is also a gravitational powerhouse, influencing the orbits of countless asteroids and comets, and is often credited with protecting the inner solar system from frequent devastating impacts by deflecting or capturing incoming debris. Its gravitational pull is a silent guardian, shaping the very environment of our cosmic neighborhood. Jupiter is accompanied by a vast retinue of moons, a miniature solar system in itself. Among them are the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, each a fascinating world. Io is the most volcanically active body in the solar system, constantly reshaped by powerful tidal forces from Jupiter. Europa, a world shrouded in a thick shell of ice, is believed to harbour a vast subsurface ocean, making it a prime candidate in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury and possesses its own magnetic field. Callisto, heavily cratered and ancient, offers a glimpse into the early history of the Jovian system, a quiet sentinel observing the grand dance. Saturn, the ringed jewel. Moving further into the cool, silent depths of space, we encounter Saturn, the breathtaking jewel of our solar system, renowned for its magnificent ethereal rings. This gas giant, though smaller than Jupiter, captivates with its unparalleled beauty, a cosmic masterpiece that invites calm contemplation. Its pale yellow and golden bands, though less vibrant than Jupiter's, speak of a serene yet powerful world. Saturn, like Jupiter, is primarily composed of hydrogen and helium, though it is less dense. In fact, if you could find a bathtub large enough, Saturn would float, as its average density is less than that of water. Its atmosphere, though less turbulent than Jupiter's, still hosts powerful storms and high-speed winds. But it is the ring system that truly defines Saturn, a spectacle of cosmic elegance. These rings are not solid structures, but are comprised of billions of individual pieces of water ice, ranging in size from microscopic dust grains to boulders as large as houses. They orbit Saturn in a precise and intricate ballet, reflecting sunlight with dazzling brilliance. The origin of Saturn's rings is a subject of ongoing scientific inquiry. Current theories suggest they may be the remnants of a shattered moon or a comet that ventured too close to the planet and was torn apart by its immense gravity. Or perhaps they are primordial material that never fully coalesced into a larger body. The rings are organized into several main groups and divisions, each maintained by the gravitational interactions with Saturn's many moons, which act as shepherds, sculpting the ring edges and maintaining their delicate structure. Saturn, too, hosts a diverse family of moons, with Titan standing out as a world of profound scientific interest. Titan is the only moon in our solar system with a dense, substantial atmosphere, even thicker than Earth's. Beneath its hazy, nitrogen-rich skies, scientists have discovered lakes and rivers of liquid methane and ethane, forming a hydrological cycle similar to Earth's water cycle, albeit with different chemistry. Another intriguing moon is Enceladus, a small icy world that spews plumes of water vapor and ice particles into space from its south pole, indicating the presence of a subsurface liquid water ocean, another promising location for potential life. Uranus, the sideways world. Our journey continues to Uranus, the 7th planet from the Sun, a world of enigmatic beauty and unique characteristics. Often referred to as an ice giant, Uranus presents a serene, blue-green hue, a result of methane in its atmosphere absorbing red light. It appears calmer than its gas giant brethren, yet holds secrets of extreme conditions. Uranus is most famous for its dramatic axial tilt. It rotates almost completely on its side, with its pole nearly pointing towards the Sun. This extreme tilt, likely caused by a colossal impact early in its history, results in extraordinary seasons, where one pole can experience decades of continuous daylight, followed by decades of darkness. Its composition differs significantly from Jupiter and Saturn. While still rich in hydrogen and helium, Uranus contains a much higher proportion of ices, such as water, ammonia, and methane, which form a superpressurized fluid ocean beneath its atmosphere. The atmosphere of Uranus, though appearing featureless to early observations, reveals faint cloud patterns and high-speed winds when observed with advanced instruments. These winds, though not as ferocious as Neptune's, are still powerful, driven by the planet's internal heat and solar radiation. Uranus also possesses a system of faint dark rings, composed of small dark particles, which are much less prominent than Saturn's. It has numerous moons, each with its own unique characteristics. Miranda, one of its larger moons, is particularly notable for its bizarre fractured surface, a chaotic jumble of cliffs, valleys, and smooth plains, suggesting a violent past of internal geological activity or fragmentation and reassembly. Neptune, the deep blue mystery, the final planetary destination on our grand tour, is Neptune, the eighth and usually farthest known planet from the Sun, a true deep blue mystery veiled in swirling clouds. This distant ice giant, named for the Roman god of the sea, perfectly embodies its namesake with its striking azure colour, intensified by the presence of methane in its atmosphere. Neptune is a world of fierce winds, the fastest in the solar system, reaching speeds of over 1,200 miles per hour. These incredible winds whip around the planet, creating dynamic and transient storm systems such as the Great Dark Spot, a massive anticyclone similar to Jupiter's Great Red Spot, though shorter-lived. Its atmosphere is cold and turbulent, with cirrus-like clouds of frozen methane. Like Uranus, Neptune's interior is believed to consist of a dense, hot fluid of water, ammonia, and methane ices surrounding a small rocky core. Discovered in 1846 through mathematical prediction, rather than direct observation, Neptune's existence confirmed the subtle gravitational influence it exerted on Uranus's orbit. It also possesses a faint ring system, composed of dark, dusty material, which is incomplete in places, forming distinct arcs rather than continuous bands. Neptune's largest moon, Triton, is a peculiar and captivating world. It orbits Neptune in a retrograde direction, meaning it travels opposite to the planet's rotation, a unique characteristic among large moons, suggesting it may be a captured Kuiper belt object, rather than having formed with Neptune. Triton is incredibly cold, with a surface temperature of around -391 degrees Fahrenheit, yet it displays active cryovolcanism, spewing plumes of nitrogen gas and dust hundreds of miles into space. These geysers hint at a dynamic internal world beneath its icy crust, a testament to the unexpected activity even in the frigid reaches of the outer solar system. Beyond the planets, the icy frontiers. As we leave the magnificent ice giants behind, our journey takes us further into the cold, silent expanses that mark the true edges of our solar system. These regions are vast, sparsely populated frontiers, filled with remnants from the system's formation, offering clues to its primordial state and the origins of comets. We enter a realm where sunlight is a distant memory, and temperatures plummet to unimaginable lows, a cosmic deep freeze. The Kuiper Belt. The icy remnants. Beyond Neptune's orbit lies the Kuiper Belt, a vast disc-shaped region of icy bodies, a sort of second asteroid belt, but much larger and composed primarily of frozen volatiles like methane, ammonia, and water. This icy frontier is home to countless small icy objects, often referred to as Kuiper Belt objects, KBOS, which are believed to be primordial remnants from the early solar system that never fully coalesced into larger planets. It is also the source of many short-period comets, those that orbit the Sun in less than 200 years. The Kuiper Belt is where we find many of our solar system's dwarf planets, including the most famous, Pluto. Once considered the 9th planet, Pluto is now recognized as a prominent member of this icy population. It is a complex and fascinating world, with a thin atmosphere that expands and collapses as it orbits the Sun, and a surprisingly diverse surface featuring mountains of water ice, vast plains of nitrogen ice, including the famous heart-shaped Sputnik Planitia, and evidence of past geological activity. Pluto is orbited by 5 known moons, with Charon being its largest, so massive that Pluto and Charon are often considered a binary system, orbiting a common centre of gravity. Other notable dwarf planets in the Kuiper Belt include Haumea and Makemake, each with their own intriguing characteristics, further illustrating the diversity of objects in this distant region. The Oort cloud, the solar system's edge. Our journey concludes at the very fringes of our solar system, a realm so distant that it exists more as a theoretical construct than a directly observed entity. The Oort cloud. This vast, spherical shell of icy objects is believed to envelop our entire solar system, extending almost a quarter of the way to the nearest star. It is the true gravitational boundary of the Sun's influence, a silent, dark reservoir of billions, perhaps trillions, of icy bodies, remnants from the very beginning of our solar system's formation. The Oort cloud is the primary source of long-period comets, those that take thousands or even millions of years to complete a single orbit around the Sun. Occasionally, a gravitational nudge from a passing star or molecular cloud can dislodge one of these icy denizens, sending it on a long, slow fall towards the inner solar system, where it eventually warms, develops its characteristic coma and tails, and becomes a visible comet. This distant, unseen region is a testament to the immense scale of our cosmic home, a vast, cold expanse where the Sun is merely the brightest star among billions. Comets, cosmic snowballs. As we contemplate the icy reservoirs of the Kuiper Belt and the Oort cloud, we understand the origin of comets, those celestial wanderers that occasionally grace our night skies. Often described as comets, are essentially cosmic conglomerates of ice, dust, and rocky particles, frozen remnants from the early solar system. When a comet's orbit brings it closer to the Sun, the solar radiation causes its icy components to sublimate, turning directly from solid to gas. This process releases dust and gas, forming a glowing halo called a coma around the comet's nucleus. The solar wind then pushes this material away from the Sun, creating the spectacular tails that can stretch for millions of miles. Comets often have 2 distinct tails, a dust tail, broad and curved, and an ion tail, straight and blue, pointing directly away from the Sun. These luminous visitors offer us direct samples of the primordial material from which our solar system was born, fleeting messengers from its distant icy frontiers. Our journey through the outer solar system, from the majestic gas giants to the icy realms of the Kuiper belt and the theoretical Oort cloud, has been a profound exploration of scale, diversity, and the enduring forces that shape our cosmic neighbourhood. We have witnessed worlds of immense power, delicate beauty, and mysterious origins, each adding another layer to the grand tapestry of our solar system. As our thoughts gently settle, we carry with us a deeper appreciation for the vastness and wonder that surrounds us, inviting a calm reflection on our place within this incredible universe. We have journeyed through the vast icy reaches of the Kuiper belt, glimpsing the enigmatic dwarf planets and the primordial, quote, 5 that are comets, those messengers from the solar system's farthest frontiers. We have drifted to the theoretical boundary of the Oort cloud, a spherical shell of icy debris that cradles our entire cosmic neighbourhood. Now, as our gentle current of knowledge brings us back toward the heart of our system, we invite you to shift your contemplation from individual worlds to the fundamental forces that orchestrate their every movement, to the grand ballet that binds them together. Allow your thoughts to settle, your breath to deepen, as we explore the invisible threads and the cosmic narratives that define our solar system as a whole. The intricate dance of planets, moons, and countless smaller bodies is not a random waltz, but a meticulously choreographed performance directed by the most pervasive force in the cosmos, gravity. This invisible hand, first understood in its profound implications by Newton, and later reshaped by Einstein's vision of space-time, is the architect of structure, the sculptor of orbits. It is gravity that pulls the planets in their elliptical paths around the sun, a continuous fall that never reaches its destination, forever looping through the void. Each celestial body, no matter how small, exerts its own gravitational pull, a subtle tug that shapes its neighbours, influencing their speed, their tilt, and their very stability. We observe that these orbital paths are not perfect circles, but ellipses, a slightly elongated curve where the Sun occupies one of two focal points. This means that at certain times a planet is closer to the Sun, perihelion, and moves faster, while at others it is farther away, aphelion, and slows its pace. This delicate balance of speed and distance maintains the stability of our system, ensuring that worlds neither spiral into the Sun nor are flung out into the cold interstellar medium. The planets generally orbit in the same direction, a testament to their shared origin from a spinning disk of gas and dust, and mostly within the same plane, a flat cosmic racetrack known as the ecliptic. Occasionally, the gravitational influence of larger bodies creates fascinating interactions. Orbital resonances occur when two orbiting bodies exert regular periodic gravitational influence on each other, usually because they have orbital periods that are simple integer ratios. We see this phenomenon at play with some of Jupiter's Galilean moons, where Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance, their regular alignments driving the immense tidal forces that heat Io's interior and fuel its volcanism. Such resonances also shape the structure of the asteroid belt, creating gaps where asteroids cannot stably orbit, and influence the distribution of objects within the Kuiper belt, offering a glimpse into the system's dynamic past. Even the Sun itself is not perfectly stationary. All the planets orbit a common Sagittarius centre. The system's centre of mass, which lies just outside or sometimes within the Sun, a subtle wobble that reveals the true interconnectedness of our cosmic family. As we contemplate these fundamental forces, we are drawn back to the radiant heart of our solar system, the Sun itself. We have observed its current glory, its ceaseless fusion, but its story, like all cosmic tales, has a beginning and an end. Our Sun is a main sequence star, a yellow dwarf, currently in the stable middle phase of its life, about 4.6 billion years old, with roughly another 5 billion years remaining in this tranquil state. It was born from the collapse of a vast cloud of gas and dust, a process we touched upon earlier, where gravitational forces compressed matter until the core became hot and dense enough to ignite nuclear fusion. But the Sun's future is as certain as its past. In approximately 5 billion years, as it exhausts the hydrogen fuel in its core, it will begin to swell, transforming into a red giant. Its outer layers will expand dramatically, cooling as they do, making the star appear reddish. Current models suggest it will expand far beyond the orbit of Mercury, likely engulfing Venus, and perhaps even Earth, turning our blue marble into a cinder before consuming it entirely. This is a distant, almost incomprehensible future, yet it is a part of the Sun's immutable stellar life cycle. Following this immense expansion, the Sun will shed its outer layers, forming a beautiful glowing shell of gas known as a planetary nebula, leaving behind its core as a dense, hot white dwarf. This stellar remnant, roughly the size of Earth but incredibly massive, will slowly cool over trillions of years, eventually becoming a cold, dark black dwarf, a final, silent testament to its once fiery existence. This grand cosmic narrative reminds us of the fleeting nature of even the most luminous stars and the immense, patient timescales of the universe. As the Sun embarks on its long journey through stellar evolution, we are reminded of the preciousness of life, a phenomenon we know exists with certainty only on one world within our system, Earth. Yet the question lingers in the quiet depths of our curiosity. Are we truly alone? This brings us to the fascinating field of astrobiology, the study of the origin, evolution, distribution, and future of life in the universe. Within our own solar system, the search for life beyond Earth primarily focuses on environments that could potentially harbour liquid water, a fundamental requirement for all known life forms. We have already observed compelling candidates. Mars, with its ancient riverbeds, deltas, and evidence of past liquid water, remains a prime target for detecting signs of ancient microbial life. Current missions, such as the Perseverance rover, actively seek biosignatures in Martian soil and rock samples. Then there are the ocean worlds of the outer solar system. Europa, one of Jupiter's Galilean moons, is believed to harbour a vast subsurface ocean beneath its icy shell, warmed by tidal forces from Jupiter. This ocean, potentially twice the volume of all Earth's oceans combined, could be a prime candidate for harbouring microbial life, protected from harmful radiation. Similarly, Enceladus, a moon of Saturn, actively vents plumes of water vapour and organic molecules from its south pole, strongly indicating a subsurface liquid water ocean interacting with a rocky core, a chemical environment tantalizingly similar to deep-sea hydrothermal vents on Earth, which teem with life. Even more exotic possibilities exist. Titan, Saturn's largest moon, with its dense atmosphere, liquid methane and ethane lakes, and complex organic chemistry, presents a unique environment where life, perhaps very different from our own, might conceivably arise. Scientists are exploring whether life could exist in non-water-based solvents, pushing the boundaries of our understanding of what constitutes habitability. The common thread in these investigations is the search for the essential ingredients: liquid water or another solvent, a source of energy, chemical or thermal, and organic molecules, the building blocks of life. Each discovery, each plume sampled, each rock analysed, brings us closer to understanding the potential for life to flourish beyond our blue marble, deepening our appreciation for the intricate conditions that allowed life to take hold here. Our journey through the solar system, from the sun's fiery core to the distant Oort cloud, has illuminated the unique characteristics of our cosmic home. But our solar system itself is not a static island in space. It is a traveller, a tiny part of a much grander structure, the Milky Way galaxy. We find ourselves nestled within one of the Milky Way's spiral arms, specifically the Orion arm, about 2/3 of the way out from the galactic centre. This vast spiral galaxy, estimated to contain between 100 billion and 400 billion stars, is our true galactic address. The solar system does not stand still. It is in constant motion, orbiting the supermassive black hole at the galactic centre, Sagittarius A star. This immense journey takes approximately 220 to 250 million Earth years to complete one full revolution, a period known as a galactic year. To put this into perspective, the last time our solar system was in its current position in the galaxy, dinosaurs were just beginning to emerge on Earth. We are currently moving at an astonishing speed of about 230 kilometers per second, 143 miles per second, relative to the galactic centre. Yet because of the immense distances involved, this motion feels imperceptible to us. Our location within the Milky Way is not arbitrary. It falls within what scientists term the galactic habitable zone. This region is considered optimal for the development of complex life, avoiding the chaotic, radiation-rich environment of the galactic core, while also being sufficiently rich in heavy elements, which are forged in stars and supernovae, necessary for planet formation and the chemistry of life. Further out, the density of stars and heavy elements decreases, making planet formation less likely. This perspective allows us to view our solar system not just as a collection of planets, but as a dynamic entity, gracefully tracing an enormous path through the cosmic tapestry of our home galaxy. As we conclude this chapter, we invite you to reflect on the profound interconnectedness of all we have explored, from the gravitational embrace that holds worlds in their dance, to the sun's majestic life cycle, to the tantalizing possibility of life hidden beneath icy shells, and finally, to our solar system's grand journey through the Milky Way. Each fact, each discovery, adds another brushstroke to the magnificent portrait of our cosmic home. Allow these images to gently settle in your mind, fostering a sense of peaceful wonder and calm contemplation. The universe is vast, intricate, and endlessly fascinating, and our small corner of it is a testament to its boundless creativity. Rest now, with these dreamy facts as your companions, knowing that the journey of discovery continues, ever expanding the horizons of our understanding. As we gently drift away from the grand scale of our galaxy, the Milky Way, and the comforting thought of our solar system's unique placement, Within its galactic habitable zone, we invite you to deepen your calm contemplation. Allow your mind to gently unfurl, like a nebula expanding in the quiet of space, as we delve into the very origins of the elements that compose us and our cosmic home. It is a journey not just through space, but through the immense tapestry of cosmic time, revealing how the universe itself is a grand, continuous cycle of creation and recreation. We embark now on an exploration of the fundamental building blocks, tracing their genesis from the fiery hearts of stars to the intricate molecular dance that forms worlds and ultimately life itself. Let this gentle current of knowledge wash over you, fostering a peaceful curiosity without demand, allowing your thoughts to drift and find stillness within the cosmic narrative. The cosmic forges, stellar nucleosynthesis. Every atom within us, every speck of dust on Earth, every mountain on Mars, and every ring particle of Saturn has a story that began long before our sun ignited. It is a tale woven in the very fabric of space-time, forged in the most extreme environments the universe has to offer. The hearts of stars. When the universe began with the Big Bang, approximately 13.8 billion years ago, it was composed almost entirely of the lightest elements, hydrogen and helium, with trace amounts of lithium. These primordial gases were the raw materials, the foundational threads for the cosmic tapestry yet to be woven. For the heavier elements, the ones that make up rocky planets, oceans, and living beings, we must look to the stars. Stars are the universe's natural alchemists, magnificent cosmic forges where lighter elements are fused into heavier ones through a process called stellar nucleosynthesis. In the cores of main sequence stars like our Sun, immense gravitational pressure and extreme temperatures ignite nuclear fusion. Here, hydrogen atoms collide and fuse, forming helium, releasing the tremendous energy that makes stars shine. This process is a slow, steady burn, a controlled cosmic fire that sustains stars for billions of years. However, the creation of elements beyond helium requires more massive and energetic stars. As larger stars exhaust their hydrogen fuel, their cores contract and heat up further, enabling the fusion of helium into carbon and oxygen. In a cascading series of nuclear reactions, progressively heavier elements are forged: neon, magnesium, silicon, and sulfur. This intricate dance of fusion continues, building elements up the periodic table until iron is formed. Iron is a crucial threshold. Fusing iron atoms actually consumes energy rather than releasing it, marking the end of a star's ability to generate energy through fusion in its core. For stars that reach this point, particularly those far more massive than our Sun, their fate is often a spectacular and violent end, a supernova. A supernova explosion is one of the most energetic events in the universe, briefly outshining entire galaxies. During these cataclysmic events, the immense shock waves and extreme conditions provide the necessary energy to create elements heavier than iron, such as gold, silver, uranium, and platinum. These precious elements, so rare on Earth, are literally stardust, born in the dying throes of colossal stars. The supernova then violently disperses this newly synthesized matter, the hydrogen, helium, and all the heavier elements, into the vastness of interstellar space, enriching the cosmic medium for future generations of stars and planetary systems. Each atom of carbon in your body, each speck of iron in your blood, was once part of an ancient exploding star. This knowledge allows for a profound sense of connection, a realization that we are truly children of the cosmos, from stardust to solar system. The journey from scattered stardust to a coherent solar system is a testament to the power of gravity and the cyclical nature of the universe. The elements forged and dispersed by supernovae do not simply vanish. They mingle with existing clouds of hydrogen and helium, forming vast, cold, and diffuse molecular clouds in interstellar space. These cosmic nurseries, rich with the legacy of dead stars, are the birthplaces of new stellar systems. Within these enormous clouds, regions of slightly higher density exist. Over eons, the omnipresent gentle pull of gravity begins its work, slowly drawing these particles closer together. Sometimes a trigger event, perhaps the shock wave from a nearby supernova, or the gravitational influence of a passing star, can compress a region within a molecular cloud, causing it to become unstable and begin to collapse more rapidly under its own gravity. As this dense core collapses, it begins to spin faster, much like an ice skater pulling in their arms. This rotation, combined with gravity, flattens the collapsing cloud into a spinning, pancake-like structure known as a protoplanetary disk, with a central, increasingly dense protostar at its heart. Our own solar system began as such a swirling disk of gas and dust approximately 4.6 billion years ago. Within this protoplanetary disk, the particles of gas and dust are not idle. They constantly collide and stick together in a process called accretion. Microscopic dust grains aggregate into larger pebbles, which then coalesce into kilometre-sized planetesimals. These planetesimals, under their mutual gravitational attraction, continue to collide and grow, gradually sweeping up material in their orbital paths. This slow, patient process of accretion, occurring over millions of years, leads to the formation of protoplanets, the embryonic versions of the worlds we know today. The conditions within the disk dictated the types of planets that would form. Closer to the fiery young sun, where temperatures were high, only rocky and metallic materials could condense. This led to the formation of the inner terrestrial planets, Mercury, Venus, Earth, and Mars. Dense, rocky worlds stripped of their lighter, volatile compounds. Further out, beyond what is known as the frost line, where temperatures were cold enough for volatile compounds like water ice, methane ice, and ammonia ice to condense, the building blocks were far more abundant. Here, massive icy cores grew rapidly, accumulating vast envelopes of hydrogen and helium gas from the surrounding disk, giving rise to the colossal gas giants like Jupiter and Saturn, and the ice giants Uranus and Neptune. This grand process of stellar and planetary formation is a continuous cycle, a cosmic recycling program where the remnants of the old become the seeds of the new, ensuring that the universe remains a dynamic and ever-evolving canvas. The building blocks of life. The creation and dispersion of elements through stellar nucleosynthesis and supernovae are not merely astronomical curiosities, they are foundational to the very existence of life. The most abundant elements created in stars, carbon, oxygen, nitrogen and hydrogen, along with phosphorus and sulfur, often referred to as CHNOPS, are the fundamental building blocks of all known life. These elements possess unique chemical properties that allow them to form complex, stable and diverse molecules, essential for biological processes. Carbon, in particular, with its ability to form 4 bonds, serves as the backbone for an incredible array of organic compounds. Scientists have observed that these crucial elements, along with water, are not confined to planets. Complex organic molecules, the precursors to life, are surprisingly common throughout the universe. They have been detected in vast interstellar clouds, within comets, and on asteroids. These molecules, ranging from simple amino acids to more complex sugars, form naturally in the cold vacuum of space, often catalyzed by ultraviolet radiation or cosmic rays. The universe, it seems, is teeming with the ingredients for life, patiently waiting for the right conditions to assemble. On the early Earth, a young, volatile world still cooling from its formation, these organic molecules, along with vast quantities of water, were likely delivered by a relentless bombardment of comets and carbonaceous asteroids. These dirty snowballs and rocky remnants, preserved from the early solar system, acted as cosmic delivery trucks, seeding our planet with the very compounds that would eventually give rise to the first self-replicating molecules. Current understanding suggests that the combination of these extraterrestrial deliveries, coupled with geological processes like hydrothermal vents on the ocean floor, provided the perfect crucible for life to spontaneously emerge. The atoms that once swirled in a distant nebula passed through the heart of an ancient star and travelled across cosmic distances, eventually found their way into the intricate structures of DNA and proteins, giving rise to the wondrous diversity of life we see today. We are quite literally made of stardust, animated by the energy of our sun and connected to the entire cosmic lineage. The dance of time, geological and cosmic scales. To truly appreciate our place within this grand cosmic narrative, we must also embrace the concept of deep time, the immense stretches of time over which cosmic and geological events unfold. Our human lives, measured in decades, are but fleeting blips on this vast timeline. Yet understanding these scales allows us to place our existence within a truly awe-inspiring context. The universe itself is approximately 13.8 billion years old, a number so immense it defies easy comprehension. If we were to compress the entire history of the universe into a single cosmic year, with the Big Bang occurring on January 1st, then our solar system would not even begin to form until early September. Our solar system, a relative newcomer, coalesced about 4.6 billion years ago. On our cosmic calendar, this places its birth around September 9th. For billions of years thereafter, the Earth slowly formed, oceans gathered, and the earliest, simplest forms of life began their hesitant dance. Complex multicellular life would not appear until mid-December on this scale, and the dinosaurs would roam the Earth only in the last few days of December. Human civilization, in this breathtaking perspective, would emerge in the final seconds of December 31st. On a more local scale, Earth's geological history stretches back billions of years, marked by the slow, inexorable movement of continents, the rise and fall of mountain ranges, and the ebb and flow of vast oceans. The rocks beneath our feet are silent witnesses to eons of change, each layer a page in Earth's ancient diary. These geological timescales reveal the patience of planetary processes, the slow grinding of erosion, the gradual accumulation of sediments, and the powerful yet infrequent volcanic eruptions that reshape landscapes over millions of years. This understanding of deep time fosters a sense of humility and wonder, reminding us of the enduring nature of cosmic forces and the precious brevity of our own moment. It encourages us to look beyond the immediate to appreciate the slow, majestic rhythm of the universe, where even the most dramatic events unfold over periods incomprehensible to our daily experience. The silent witnesses, asteroids, comets, and meteorites as time capsules. As we contemplate the grand sweep of cosmic time and the origins of matter, we find invaluable clues in the most unassuming of celestial objects, the asteroids, comets, and meteorites that silently traverse our solar system. These are not merely random pieces of debris. They are pristine time capsules, remnants from the very dawn of our solar system, preserving the conditions and composition of the primordial solar nebula. Studying them is akin to opening an ancient archive, offering direct insights into the processes that formed our sun and planets. Asteroids, predominantly found in the Thane asteroid belt between Mars and Jupiter, are rocky and metallic fragments that largely failed to coalesce into a full-sized planet. Their compositions vary, from stony silicates to rich metallic cores, reflecting the conditions and materials present at different distances from the early Sun. Many asteroids have remained largely unchanged since their formation 4.6 billion years ago, providing snapshots of the raw material from which the terrestrial planets were built. Scientists meticulously study their spectral signatures and analyze samples brought back by probes or found as meteorites on Earth, revealing details about the temperature, pressure, and chemical makeup of the nascent solar system. They are the leftovers, the unbaked ingredients of planetary formation, offering a direct window into the past. Comets, on the other hand, are icy wanderers hailing from the frigid distant reaches of our solar system, the Kuiper belt and the even more remote Oort cloud. Often described as dirty snowballs, they are composed of a mixture of water ice, frozen gases like carbon dioxide and methane, and dust, including complex organic molecules. Unlike asteroids, which formed closer to the Sun, comets have spent billions of years in the deep freeze of outer space, preserving the most volatile and pristine materials from the original solar nebula. When their elliptical orbits bring them closer to the Sun, their icy components sublimate, releasing gas and dust to form the spectacular coma and tails that make them visible. The study of cometary material, whether through telescopic observation, space probes, or analysis of certain meteorites, provides crucial information about the initial chemical inventory of the solar system, including the source of Earth's water and a significant portion of its organic molecules. Meteorites are the fragments of asteroids or comets that survive their fiery descent through Earth's atmosphere and land on our planet. These tangible pieces of other worlds are perhaps our most direct connection to the early solar system. Among them, carbonaceous chondrites are particularly prized. These dark primitive meteorites are rich in carbon and contain water-bearing minerals, as well as a complex array of organic compounds, including amino acids, the building blocks of proteins. Their presence on Earth provides compelling evidence that the ingredients for life were readily available in the early solar system and were delivered to our nascent planet, setting the stage for life's emergence. These silent witnesses, these cosmic messengers, whisper tales of creation, telling us not only where we came from, but also about the universal processes that shape worlds across the cosmos. As we conclude this chapter, allowing these profound insights to settle softly within your mind, we hope you feel a deeper connection to the grand cosmic ballet. You are quite literally stardust, born from the fiery hearts of ancient suns, shaped by the gentle hand of gravity and carried through billions of years of cosmic evolution. Rest in this knowledge, allowing your thoughts to drift and find stillness, knowing that the universe is not only vast and mysterious, but also intimately connected to every atom within you. We invite you to carry this peaceful curiosity with you as we prepare for our next gentle exploration into the wonders that wait. We invite you once more to settle into this gentle current of knowledge, allowing your thoughts to drift and find stillness as we continue our journey through the vast and wondrous expanse of our cosmic home. In our previous contemplations, we observed the universe's most ancient elements coalescing into stars, witnessed the birth of our sun and its planets from a swirling protoplanetary disk, and marveled at the cosmic debris, asteroids, comets, meteorites that serve as invaluable time capsules, preserving the primordial ingredients of our solar system and perhaps the very seeds of life. Now, we turn our gaze to the incredible ingenuity and relentless curiosity that allow us to decipher these cosmic messages, to reach out across the void, and to envision the long unfolding future of our celestial neighborhood. How do we, mere inhabitants of a single blue marble, come to understand the fiery heart of our sun, the intricate dance of distant worlds, or the icy breath of a comet? We do so through the extension of our senses, through the patient craft of observation, and the bold spirit of exploration. Our journey of discovery begins not with a physical step into space, but with a gaze skyward, amplified by the marvels of observational astronomy. From the earliest stargazers who charted the heavens with their naked eyes, humanity has sought to understand the celestial tapestry above. Today, our tools are far more sophisticated, allowing us to capture light and other forms of electromagnetic radiation that travel billions of miles to reach us. Telescopes. Both grand terrestrial behemoths and orbiting sentinels act as our cosmic eyes. Ground-based optical telescopes, often nestled atop remote mountains to escape atmospheric interference, gather the faint whispers of light from distant galaxies and the subtle gleam reflecting off planets within our own system. Their mirrors, polished to incredible precision, collect and focus photons, revealing details previously unimaginable. Yet, Earth's atmosphere, while vital for life, acts as a veil, absorbing much of the electromagnetic spectrum. This is where space-based observatories become indispensable. Freed from the atmospheric shroud, telescopes like the venerable Hubble Space Telescope have offered us breathtaking vistas of nebulae, galaxies, and the detailed surfaces of planets. More recently, the James Webb Space Telescope, JWST, operating in infrared light, pierces through cosmic dust clouds to reveal the birth of stars and the formation of early galaxies, offering new insights into the very origins of the universe, and even detecting the atmospheric compositions of exoplanets far beyond our solar system. Radio telescopes, with their vast dishes, listen to the universe in wavelengths invisible to the human eye, detecting everything from the faint hum of the Big Bang's afterglow to the energetic emissions from distant quasars and the subtle signals from pulsars within our own galaxy. They allow us to map the distribution of gas and dust, revealing the skeletal structures of galaxies and the birthplaces of stars. Beyond simply seeing, we learn through spectroscopy, the art of dissecting light. When light from a celestial object is passed through a prism or diffraction grating, it separates into its constituent colours, much like a rainbow. Within this spectrum lie telltale dark or bright lines, unique fingerprints left by the elements present in the object's atmosphere or surface. By analysing these spectral lines, scientists can determine the chemical composition of stars, planets and nebulae, measure their temperature, discern their velocity towards or away from us, the Doppler effect, and even infer the presence of magnetic fields. It is through spectroscopy that we know the Sun is primarily hydrogen and helium, that Venus's atmosphere is thick with carbon dioxide, and that distant exoplanets possess atmospheres that might someday reveal signs of life. But observation, no matter how powerful, can only take us so far. To truly understand our cosmic neighbours, we must touch them, taste them, measure them directly. This is the realm of space exploration, a testament to humanity's audacious spirit. The dawn of the space age saw the launch of pioneering probes that expanded our understanding beyond Earth's immediate vicinity. The Voyager probes, launched in the late 1970s, embarked on a grand tour of the outer planets, sending back the first detailed images of Jupiter, Saturn, Uranus, and Neptune, forever transforming our view of these gas and ice giants. Today, they continue their silent journey into interstellar space, carrying a golden record, a message in a bottle from humanity to any potential cosmic recipients. In subsequent decades, a fleet of robotic explorers has meticulously investigated almost every corner of our solar system. Orbiters like Galileo at Jupiter, Cassini at Saturn, and Juno, currently circling Jupiter, have provided unprecedented data on their atmospheres, magnetospheres, and moons, revealing hidden oceans beneath icy shells and dynamic meteorological phenomena. Landers and rovers, most notably on Mars, from the early Vikings to the Spirit, Opportunity, Curiosity, and Perseverance rovers, have trundled across alien landscapes, drilling into rocks, analysing soil, and searching for evidence of past or present life, painting a vivid picture of the red planet's geological history and its potential for habitability. The New Horizons probe, after its flyby of Pluto and the Kuiper Belt object Arakoth, demonstrated our ability to reach the most distant, frigid outposts of our system, revealing worlds far more complex and geologically active than previously imagined. And then there is the enduring dream of human space exploration. The Apollo missions, which landed humans on the Moon, represented a monumental leap for humankind, demonstrating our capacity for incredible feats of engineering and courage. Today, the International Space Station, ISS, serves as a permanent orbiting laboratory, a beacon of international cooperation, where astronauts conduct scientific research in microgravity, preparing for longer duration missions. The future calls us further. Programs like Artemis aim to return humans to the Moon, establishing a sustainable presence that will serve as a stepping stone for the ultimate journey, sending humans to Mars. These endeavours are not merely about planting flags, they are about pushing the boundaries of human knowledge, fostering innovation, and perhaps ensuring the long-term survival of our species by becoming a multi-planetary civilization. As we delve deeper into our solar system, we also confront the vastness of what remains unknown, the unseen and the mysterious that continue to beckon us forward. The Kuiper belt and the Oort cloud, though extensively theorized, still hold countless undiscovered objects, icy remnants that could offer further clues about the solar system's early days. The gravitational anomalies observed in the outer reaches of our system have led to the tantalizing hypothesis of a distant, as yet undiscovered, Planet 9, a world potentially larger than Earth, subtly shaping the orbits of smaller icy bodies. Our understanding of planet formation, while robust, is constantly being refined, with new exoplanetary discoveries challenging existing models and pushing us to consider a wider array of possibilities for how worlds come into being. The precise mechanisms that led to the emergence of life on Earth, and whether those same conditions exist or have existed elsewhere in our solar system, remain profound, active areas of scientific inquiry. These ongoing mysteries remind us that our journey of discovery is never truly complete. Each answered question often uncovers a dozen more, propelling us further into the cosmic unknown with renewed vigor and curiosity. Finally, as we contemplate these grand cycles of formation and discovery, we are drawn to reflect on the long arc of time that stretches far beyond our current moment, into the solar system's distant future. We have already considered the Sun's ultimate fate, its expansion into a red giant, engulfing the inner planets, and its eventual cooling into a white dwarf. But what of the remaining planets and the solar system as a whole in those unimaginably distant eons? Even after the Sun's stellar core ceases to burn, its gravitational influence will persist, albeit diminished. The gas giants and the icy worlds of the outer solar system will continue their orbits around the faint ember of the white dwarf. Over truly immense timescales, billions, even trillions of years, subtle gravitational perturbations, collisions with interstellar objects, and the gradual loss of orbital energy could slowly reshape the system. Planets might be nudged into new orbits, some potentially ejected into the cold embrace of interstellar space, while others might spiral inward towards the cooling stellar remnant. The Kuiper belt and Oort cloud, once vibrant nurseries of comets, will thin out, their icy inhabitants either flung away or gradually vaporized by the faint radiation from the white dwarf. Eventually, as the white dwarf itself cools over countless eons, becoming a black dwarf, a theoretical, truly dark and cold stellar corpse, the solar system will become an even more desolate and silent place. The intricate dynamic ballet of planets and moons that we witness today will have faded into a slow, almost imperceptible drift. This ultimate future paints a picture of profound cosmic solitude, a testament to the impermanence of even the grandest structures in the universe, yet also highlighting the precious fleeting vibrancy of the present moment. As we gently return from this contemplation of deep time and distant futures, we hope you feel a renewed sense of connection to this incredible cosmic tapestry. From the whispers of ancient starlight to the bold leaps of modern exploration, from the building blocks of life to the ultimate fate of our solar system, we are all part of an ongoing, awe-inspiring story. Allow the facts to settle, not as burdens to be remembered, but as gentle currents carrying you into a state of peaceful curiosity and tranquil wonder. We invite you to find stillness in this vastness, knowing that even in the quietest moments, the universe continues its grand, silent dance. As we gently drift away from the contemplation of our sun's ultimate distant solitude, we're invited to refocus on the vibrant present, a present brimming with the ceaseless dance of discovery. While our cosmic home, the solar system, holds countless wonders and a defined future, it is but one island in an ocean of stars, a single narrative within an epic cosmic saga. Our journey of understanding does not end at the icy frontiers of the Oort cloud, nor does it conclude with the final whisper of a dying star. Instead, it expands, pushing the boundaries of our perception outward into the vast, star-strewn expanse of our galaxy and beyond. We now turn our collective gaze towards those distant suns, each a potential beacon for other worlds, other stories. The question that has echoed through human history, "Are we alone?" has transformed from a philosophical musing into a vibrant field of scientific inquiry, the search for exoplanets. These are worlds orbiting stars other than our Sun, and their discovery has reshaped our understanding of planetary formation and the prevalence of cosmic real estate. The quest for exoplanets is a testament to human ingenuity, employing a suite of sophisticated techniques to detect these often elusive celestial bodies. One of the most successful methods is the transit method, where scientists observe a slight periodic dimming of a star's light as an orbiting planet passes directly in front of it from our vantage point. Each dip in brightness, a tiny eclipse, reveals the planet's presence, its size relative to its star, and the duration of its orbit. Missions like NASA's Kepler Space Telescope and TS, Transiting Exoplanet Survey Satellite, have revolutionized this field, cataloguing thousands of such transits, each a distant world momentarily revealing itself. Another powerful technique is the radial velocity method, also known as the Doppler wobble method. As a planet orbits its star, its gravitational pull causes the star to subtly wobble. This wobble, though minuscule, can be detected by observing shifts in the star's light spectrum, a phenomenon known as the Doppler effect. If the star moves towards us, its light shifts towards blue. If it moves away, its light shifts towards red. By meticulously measuring these shifts, astronomers can infer the presence of an orbiting planet, estimate its mass, and determine its orbital period. More recently, advancements in instrumentation have allowed for direct imaging of some exoplanets, particularly large, hot young worlds located far from their parent stars. This incredibly challenging feat involves blocking out the overwhelming glare of the star to capture the faint light, reflecting off or emitted by the planet itself. Each successful direct image offers an unprecedented glimpse into the atmospheres and characteristics of these distant worlds. Furthermore, the burgeoning field of gravitational lensing provides another window, where the gravity of a foreground star or galaxy can magnify the light from a background star, sometimes revealing the presence of unseen planets around the foreground object. What these diverse methods reveal is a staggering variety of planetary systems, far exceeding the initial expectations based solely on our solar system. We have discovered hot Jupiters, gas giants orbiting incredibly close to their stars, completing a year in just a few Earth days. There are super-Earths, rocky worlds larger than Earth but smaller than Neptune, a class of planet not found in our own solar system. Mini-Neptunes, similar in size but potentially with different compositions, also populate the exoplanet catalogue. Some planets are so distant from their stars, or have been ejected from their systems, that they roam the interstellar void as rogue planets, adrift in the galactic night, warmed only by their internal heat. This cosmic menagerie continually challenges and refines our theories of planetary formation. Among this vast collection, the most captivating are those worlds residing within their star's habitable zone, the region around a star where conditions are theoretically right for liquid water to exist on a planet's surface. This quote, 11 is neither too hot, causing water to evaporate, nor too cold, freezing it solid. While the presence of liquid water is considered a key ingredient for life as we know it, it is not the sole determinant. A planet's atmospheric composition, magnetic field, geological activity, and even the type of star it orbits, its variability and flare activity, all play crucial roles in determining its true habitability. The ultimate goal of exoplanet research is the search for biosignatures, chemical indicators in a planet's atmosphere or on its surface that suggest the presence of life. Oxygen, methane, and ozone, for example, if detected in significant quantities and specific ratios, could hint at biological processes. Future space telescopes, like the James Webb Space Telescope and its successors, are poised to push the boundaries of this search, capable of analyzing the light passing through exoplanet atmospheres to detect these tantalizing clues. Systems like TRAPPIST-1, with its 7 Earth-sized planets, several of which lie within the habitable zone of their ultra-cool dwarf star, offer compelling targets for such detailed atmospheric studies. As we expand our vision to these myriad worlds, we inevitably zoom out further, placing our own solar system and its newly discovered cousins within their grander context, the Milky Way galaxy. Our solar system is but a speck, located in one of the outer spiral arms, the Orion arm, of this majestic barred spiral galaxy. The Milky Way is a colossal island of stars, gas, dust, and dark matter, spanning approximately 100,000 light-years in diameter and containing an estimated 100 to 400 billion stars. From our vantage point within it, we perceive the Milky Way as a luminous band across the night sky, a river of light woven from countless distant suns. Its structure is intricate and dynamic, dominated by a central bar of stars from which several prominent spiral arms gracefully unfurl. These arms are regions of enhanced star formation, glowing with the brilliance of young, hot blue stars and nebulae, the stellar nurseries where new suns and planets are born from vast clouds of gas and dust. Our solar system orbits the galactic center at a speed of about 230 kilometers per second, completing one full revolution roughly every 230 million years. A quote, 12 at the very heart of the Milky Way, veiled by thick clouds of gas and dust, lies Sagittarius A, pronounced, quote, thirsty, a supermassive black hole with a mass equivalent to about 4 million suns. This cosmic behemoth exerts an immense gravitational pull, dictating the orbits of stars and gas clouds in its vicinity, and playing a fundamental role in the dynamics of the entire galaxy. While its presence is awe-inspiring, it is also a quiet giant, not actively consuming matter, and thus not posing a threat to our distant solar system. The Milky Way is not an isolated entity. It is part of a larger cosmic neighborhood known as the Local Group, a collection of over 50 galaxies gravitationally bound together. Our largest galactic neighbours include the Andromeda Galaxy, a magnificent spiral even larger than the Milky Way, and the Triangulum Galaxy, These three large spirals, along with numerous dwarf galaxies, are slowly but inexorably drawing closer. In several billion years, the Milky Way and Andromeda are destined for a spectacular, albeit slow motion, collision and merger, forming a new, larger elliptical galaxy, which scientists have playfully dubbed, quote, 14. This contemplation of galactic scales leads us to the ultimate canvas, the universe itself. The Milky Way is just one of an estimated 2 trillion galaxies in the observable universe, each a sprawling metropolis of stars. These galaxies are not randomly scattered, but are organized into a vast, intricate cosmic web of clusters and superclusters, separated by immense voids. Our current understanding of the universe's origin is encapsulated in the Lambda Big Bang theory, which posits that the universe began approximately 13.8 billion years ago from an extremely hot, dense state, and has been expanding and cooling ever since. The evidence supporting this theory is compelling. One of the most significant pieces of evidence is the cosmic microwave background, CM. Radiation, a faint glow of microwave light permeating all of space. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old before light could freely travel. Its uniform temperature, with tiny fluctuations, tells us about the early universe's composition and structure, providing the seeds for the galaxies we observe today. As the universe expanded and cooled, matter coalesced under gravity, forming the first stars and galaxies. Yet, our observations reveal that the visible matter, the stars, planets, gas and dust, accounts for only about 5% of the universe's total mass-energy content. The remaining 95% is composed of two mysterious components: dark matter and dark energy. Dark matter, making up about 27% of the universe, does not interact with light or other electromagnetic radiation, making it invisible to our telescopes. However, its gravitational influence is profound. It holds galaxies together, preventing them from flying apart as they rotate, and shapes the large-scale structure of the cosmic web. Scientists infer its existence from its gravitational effects on visible matter, but its true nature remains one of the universe's most profound unsolved mysteries. Various candidates, from exotic particles to primordial black holes, are actively being explored. Even more enigmatic is our own dark energy, which constitutes approximately 68% of the universe. Far from merely shaping structures, dark energy is responsible for the accelerating expansion of the universe. For billions of years, gravity was thought to be slowing the universe's expansion, but observations in the late 1990s revealed that the expansion is actually speeding up. Dark energy is hypothesized to be a repulsive force intrinsic to space itself, pushing galaxies apart. Its nature is even less understood than dark matter, representing a fundamental gap in our understanding of physics. These unseen forces, dark matter and dark energy, are the silent, invisible architects of the cosmos, shaping its destiny on the grander scales. They remind us that for all our advancements, the universe still holds vast realms of the unknown, beckoning us to continue our journey of inquiry. As we contemplate these immense scales, from the tiny wobble of an exoplanet star to the accelerating expansion of the entire universe, we are reminded that our scientific journey is a continuous process. Each discovery opens new questions, Each answer illuminates new pathways of exploration. The next generation of telescopes, both ground-based and spaceborne, will undoubtedly reveal even more wonders, pushing the boundaries of what we currently believe possible. We are in an era of unprecedented discovery, constantly refining our models, challenging our assumptions, and expanding our cosmic perspective. In this vast, dynamic, and largely mysterious universe, our solar system is a familiar haven, a cosmic home that we're only beginning to fully comprehend. Yet its story is intertwined with the stories of countless other worlds, other stars, and the grand unfolding narrative of the cosmos itself. We invite you to let these thoughts drift, to find a peaceful curiosity in the knowledge that we are part of something so immeasurably vast and wondrous, a silent, tranquil participant in the universe's eternal dance of creation and evolution. We drift now beyond the familiar glow of our sun, past the furthest icy frontiers and the lingering whispers of the Oort cloud, to where the fabric of the cosmos itself begins to reveal its deepest enigmas. Our journey through the solar system has unveiled worlds of vibrant contrast and intricate design, each bound by the fundamental forces we have come to understand. Yet, as we cast our gaze further into the grand tapestry of the universe, we encounter phenomena that challenge our perceptions and beckon us into realms of profound mystery. It is here, in the vast, silent expanse, that we meet the unseen architects of the cosmos. Dark matter and dark energy. Allow your thoughts to settle like cosmic dust in a nebula as we explore these invisible forces that shape galaxies and dictate the very destiny of existence. This is not a journey into the known, but an invitation to contemplate the edges of our understanding, to embrace the peaceful curiosity that arises when faced with the truly unknown. Our current understanding suggests that the visible matter, the stars, planets, gas, and dust that compose everything we can observe and interact with, accounts for a mere 5% of the universe's total mass energy content. The remaining 95% is a profound enigma, divided between what scientists call dark matter and dark energy. We begin with dark matter, a mysterious substance that does not emit, absorb, or reflect light, rendering it utterly invisible to our telescopes and detectors. Yet, its presence is profoundly felt through its gravitational influence. Imagine a cosmic ghost, unseen but undeniably present, tugging at galaxies, holding them together with an invisible embrace. This is, in essence, how scientists have deduced the existence of dark matter. One of the most compelling pieces of evidence comes from observing the rotation of galaxies. If galaxies were composed only of the visible matter we see, their outer regions would spin much slower, flinging stars into intergalactic space, much like a carousel spinning too fast would eject its riders. Instead, spiral galaxies rotate at speeds that indicate a tremendous amount of unseen mass is providing additional gravitational pull, holding them intact. This invisible halo of mass, extending far beyond the visible spiral arms, is attributed to dark matter. Further evidence emerges from the phenomenon of gravitational lensing. Just as a glass lens bends light, massive objects in space can warp space-time, causing the light from distant galaxies to bend and magnify as it passes by. When astronomers observe clusters of galaxies, they find that the amount of lensing is far greater than what can be explained by the visible matter alone. This excess lensing points to vast reservoirs of dark matter nestled within these clusters, acting as an invisible scaffold upon which galaxies gather and evolve. It is a silent, gravitational anchor, preventing the universe's grand structures from unraveling. The nature of dark matter remains one of cosmology's most significant puzzles. Current theories propose several candidates, though none have been definitively confirmed. One leading hypothesis suggests it consists of weakly interacting massive particles, or WIMPs, a class of hypothetical particles that interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Another possibility involves axions, ultra-light particles also predicted by some theories. Less favoured, but historically considered, were MACHOs, massive astrophysical compact halo objects, which included stellar mass black holes, brown dwarfs, or rogue planets. However, extensive searches for these objects through micro-lensing experiments have largely ruled them out as the primary component of dark matter. The quest to directly detect dark matter particles on Earth, deep underground to shield them from cosmic radiation, continues with unwavering dedication, a testament to humanity's relentless pursuit of knowledge. From the unseen gravitational embrace of dark matter, we now turn our attention to an even more enigmatic force: dark energy. If dark matter acts as a cosmic glue, holding structures together, dark energy appears to be a cosmic anti-gravity, pushing everything apart. It is the mysterious force responsible for the accelerating expansion of the universe. For decades, scientists believed that the universe's expansion, initiated by the Big Bang, would gradually slow down due either to the collective gravity of all matter within it, or perhaps even reverse, leading to a quote 15. However, groundbreaking observations in the late 1990s, particularly of distant Type Ia supernovae, standard candles whose intrinsic brightness is known, revealed a startling truth. These supernovae, acting as cosmic mile markers, appeared dimmer and therefore further away than expected for a decelerating universe. The only logical conclusion was that the expansion of the universe was not slowing down, but rather speeding up. This discovery was revolutionary, earning a Nobel Prize and fundamentally altering our understanding of the cosmos. It implies the existence of a pervasive repulsive force woven into the very fabric of space-time, a force we call dark energy. Unlike dark matter, which clumps around galaxies, dark energy is thought to be uniformly distributed throughout the universe, its influence growing as space itself expands. It is a constant, subtle push, gradually overcoming the gravitational pull of matter and causing the galaxies to recede from one another at an ever-increasing rate. The precise nature of dark energy is even more elusive than that of dark matter. The simplest and most widely accepted explanation is that it is a cosmological constant, an intrinsic property of empty space itself, first proposed by Albert Einstein in his general theory of relativity, though he later called it his quote 16 when he thought the universe was static. This quote 17 would exert a constant outward pressure. Other, more speculative theories suggest that dark energy might be a dynamic, evolving field, dubbed quote 18, whose strength varies over time. Regardless of its exact identity, dark energy represents approximately 68% of the total mass energy of the universe, dwarfing both dark matter and visible matter in its cosmic significance. As we contemplate these two dominant yet invisible components of our universe, we begin to grasp the profound implications for its ultimate destiny. The interplay between gravity, dark matter, and dark energy will determine the final chapter of cosmic evolution. If dark energy continues its relentless push, the universe faces a future known as the quote, das heißt die Stern, or quote, strong. In this scenario, galaxies will continue to move apart at an accelerating pace, eventually becoming so distant that their light will never reach us. Stars will burn out, black holes will evaporate over unimaginably vast timescales through Hawking radiation, and the universe will become an increasingly cold, dark and empty void, reaching a state of maximum entropy where no energy can be extracted to do work. The grand cosmic ballet will slowly fade into an eternal, frigid stillness. Another, more extreme, possibility related to dark energy is the quote 21 quote. If dark energy were to strengthen over time, its repulsive force could eventually overcome all other fundamental forces. First, galaxies would be torn apart, then star systems, then planets, and finally, even atoms themselves would be ripped asunder, leaving behind only elementary particles in an infinitely expanding, desolate void. Current observations, however, lean more towards the Big Freeze scenario, suggesting that dark energy is more consistent with the cosmological constant rather than an escalating force. Conversely, if the density of matter and dark matter were high enough to eventually overcome the effects of dark energy, the universe's expansion could halt and reverse, leading to a big crunch. In this scenario, all matter would eventually collapse back into an infinitely dense hot state, perhaps similar to the conditions at the Big Bang, potentially leading to a new cycle of creation. However, current data overwhelmingly points to an open, expanding universe, making the Big Crunch seem increasingly unlikely. We return now to the tranquil stillness of our contemplation, allowing these vast, mind-bending concepts to settle gently within our awareness. The journey through our solar system has shown us the intricate beauty of our immediate cosmic neighborhood. The exploration of dark matter and dark energy expands that beauty to the largest possible scales, revealing that even the empty space between galaxies is teeming with profound mysteries, shaping the very evolution of time and existence. We are, in essence, voyagers on a cosmic ocean, charting known islands while always aware of the vast, unexplored depths that lie beyond. The existence of dark matter and dark energy underscores the humility inherent in scientific discovery. The more we learn, the more we realize how much more there is to discover. It is a continuous unfolding, a grand narrative that we are only just beginning to read. As your thoughts drift, finding stillness in the contemplation of these cosmic architects, remember that this journey is not about memorization, but about peaceful wonder. It is about allowing the mind to expand, to embrace the vastness and the mystery, and to find a quiet sense of belonging within this incredible, expanding universe. Our solar system, our planet, our very existence are all woven into this grand, unseen design, and in that realization there is a deep and abiding peace. The search for understanding continues, a beacon of human curiosity shining brightly even in the face of the universe's most profound secrets. As we contemplate the universe's ultimate, perhaps chilling destiny, a slow fade into the Big Freeze, a realm of infinite emptiness and cold, we are reminded of the profound journey of discovery that has brought us to this understanding. This cosmic narrative, unfolding across billions of years and unimaginable distances, is not merely a collection of facts. It is a reflection of our enduring curiosity, a testament to the human spirit that dares to look up and ask why. We invite you now to turn your gaze inward, to consider the echoes of discovery within us, and the pathways we continue to forge into the unknown. Our journey through the solar system and beyond has revealed a universe of breathtaking complexity and unexpected beauty, from the sun's fiery heart to the icy reaches of the Oort cloud, from the intricate dance of galaxies to the elusive whispers of dark matter and dark energy. We have traversed realms that once existed only in the wildest imaginings. Yet, with every answer uncovered, a new constellation of questions emerges, beckoning us further into the cosmic tapestry. This relentless pursuit of knowledge is a defining characteristic of our species, a gentle current of inquiry that propels us forward, ever seeking to comprehend our place in this grand unfolding story. The tools of our exploration become ever more sophisticated, extending our senses across impossible gulfs of space and time. We have moved beyond the simple lens, now harnessing the very fabric of space-time and the most elusive particles to paint a more complete picture of reality. Consider the James Webb Space Telescope, JWST, a marvel of engineering, often described as a golden eye peering through cosmic dust. Launched into an orbit far beyond Earth's disruptive heat, JWST observes the universe primarily in infrared light, allowing it to penetrate the veils of gas and dust that obscure visible light. This capability is revolutionary, enabling us to witness the very first galaxies forming in the infant universe, observe the birth of stars and planetary systems within dense nebulae, and even analyze the atmospheres of distant exoplanets for potential biosignatures. Its images, imbued with an ethereal glow, reveal a universe vibrant with nascent light, pushing the boundaries of what we thought was observable, inviting us to contemplate the very dawn of creation. On Earth, a new generation of extremely large telescopes, ELTs, is under construction, pushing the limits of ground-based astronomy. Imagine mirrors tens of meters in diameter, equipped with adaptive optics that correct for atmospheric distortions in real time. This extremely large telescope, EL Taurus in Chile for instance, will boast a primary mirror nearly 39 meters wide, designed to gather more light and resolve finer details than any optical telescope before it. These colossal instruments will be able to directly image exoplanets, resolve individual stars in nearby galaxies with unprecedented clarity, and search for the elusive quote 24 quote of the universe, offering complementary insights to space-based observatories. They are monuments to our collective ambition, allowing us to delve into the intricate structure of galaxies, scrutinize the behavior of black holes, and perhaps even test the fundamental laws of physics with greater precision. Beyond the electromagnetic spectrum, we have opened entirely new windows onto the cosmos: the Laser Interferometer, Gravitational Wave Observatory, LIGO, and its partners, Virgo and Cagra, have ushered in the era of gravitational wave astronomy. For centuries, our understanding of the universe relied solely on light, electromagnetic radiation. But now, we can quote 25 the universe, detecting the faint ripples in space-time caused by cataclysmic events. The merger of black holes, the collision of neutron stars, and perhaps even the echoes of the Big Bang itself. These gravitational waves offer a unique perspective, travelling unimpeded through matter and revealing phenomena that are otherwise invisible. They are the universe's most profound symphony, a chorus of cosmic violence and creation, allowing us to probe the most extreme environments and test Einstein's theory of general relativity with exquisite accuracy. Even more elusive are neutrinos, tiny, nearly massless particles that interact very weakly with matter. Born from nuclear reactions in stars, supernova, and even the Big Bang, neutrinos carry direct information from the hearts of these extreme events. Observatories buried deep underground or submerged in ice, like IceCube at the South Pole, are designed to detect these ghost-like particles. By observing high-energy cosmic neutrinos, we gain insights into the most powerful accelerators in the universe: blazars, active galactic nuclei, and gamma-ray bursts, unveiling processes that shape the cosmos in ways we are only beginning to comprehend. Each new messenger, light, gravitational waves, neutrinos, adds another layer to our cosmic understanding, weaving a richer, more vibrant tapestry of reality. Our thirst for direct exploration also continues unabated, particularly within our own solar system. The Artemis program represents a renewed commitment to human spaceflight, aiming to return humans to the Moon and establish a sustainable lunar presence. The Lunar Gateway, a small space station orbiting the Moon, will serve as a vital stepping stone, enabling longer duration missions to the lunar surface and acting as a staging ground for deeper space exploration, including future human missions to Mars. These endeavours are not merely about planting flags. They are about learning to live and work off-world, developing the technologies and expertise necessary for humanity's expansion beyond Earth. Robotic missions continue to push the boundaries of our understanding of potential life beyond Earth. The Europa Clipper mission, currently in development, will conduct detailed reconnaissance of Jupiter's moon Europa, a prime candidate for harbouring a subsurface ocean beneath its icy shell. It will fly by Europa numerous times, studying its ocean, ice shell, composition and geology, searching for plumes of water vapour that could offer direct access to its hidden liquid realm. Similarly, the Dragonfly mission is slated to send a rotorcraft lander to Saturn's moon Titan, a world with a dense atmosphere and lakes of liquid methane and ethane. Dragonfly will explore Titan's diverse environments, studying its complex organic chemistry and searching for the building blocks of life in a very different chemical environment than Earth's. These missions are profound acts of scientific curiosity, reaching out to touch worlds where life, in forms we might not yet recognize, could potentially thrive. Looking even further, the dream of interstellar exploration remains a powerful motivator. While immense technological hurdles remain, concepts like Breakthrough Starshot envision tiny, light-sail-propelled probes that could reach nearby star systems within decades, capturing images and data from exoplanets. Such audacious projects, though still in their infancy, represent the ultimate expression of our drive to explore, to transcend the boundaries of our solar system and touch the stars themselves, to verify if other suns indeed host other worlds, and perhaps other forms of life. This ever-expanding cosmic knowledge inevitably leads us to profound philosophical contemplation. What does it mean to be human in a universe so vast, so ancient, and so mysterious? The pale blue dot perspective, famously articulated by Carl Sagan, reminds us of Earth's fragility and uniqueness, a vibrant oasis suspended in the indifferent void. This perspective fosters a sense of humility, interconnectedness, and a renewed appreciation for the delicate balance that allows life to flourish here. It underscores our responsibility as stewards of this precious planet, the only home we truly know, the search for extraterrestrial life, fueled by the discovery of thousands of exoplanets, reignites ancient questions about our solitude or companionship in the cosmos. Is life a cosmic commonplace, or a rare, precious phenomenon? The Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the lack of observational evidence, continues to challenge our assumptions. Are we simply too early, too far, or are there filters that prevent intelligent life from emerging or expanding? These questions, though currently without definitive answers, propel our scientific inquiry and deepen our understanding of life's origins and evolution. Ultimately, our journey through the solar system and the universe is an unending one. Every answer we uncover serves not as an end point, but as a new beginning, revealing deeper layers of complexity and beauty. The cosmos remains an eternal source of wonder, a canvas of infinite possibilities that invites our peaceful curiosity and calm contemplation. As we continue to gaze upward, to listen to the universe's whispers, and to reach out with our instruments, we are not just exploring the stars, we are exploring ourselves, reflecting on our place in the grand cosmic ballet, and affirming the enduring human spirit of inquiry. The universe, in its vastness and mystery, continues to be our greatest teacher, offering not just facts, but a profound sense of peace and belonging within its wondrous expanse. As our journey through the cosmic expanse continues, we invite you once more to settle into a state of tranquil contemplation. Allow the gentle current of knowledge to carry you, not demanding recall, but fostering a peaceful curiosity. We have traced the arcs of planets, witnessed the birth and death of stars, and pondered the invisible forces that sculpt galaxies. Yet, beneath these observable phenomena lie even deeper mysteries, fundamental principles that govern the very fabric of existence. Today, we delve into the profound architecture of space-time itself, exploring how gravity, the force that binds our solar system, is in fact a symphony played on the universe's most exquisite instrument. We begin by shifting our understanding of gravity from a mere pulling force to a fundamental curvature of space-time. Imagine, if you will, space-time not as an empty void, but as an invisible, flexible tapestry woven throughout the cosmos. This revolutionary concept, gifted to us by Albert Einstein's theory of general relativity, suggests that massive objects do not simply exert a pull on others. Instead, they warp and distort this cosmic fabric around them, much like a bowling ball placed on a stretched rubber sheet. Other objects encountering these distortions simply follow the curves in the fabric, giving us the illusion of attraction. This elegant dance of mass and curvature dictates the path of every comet, the orbit of every planet, and the grand spiral of every galaxy. This curvature of space-time manifests in astonishing ways. One such phenomenon is gravitational lensing, where the immense gravity of a massive galaxy or cluster of galaxies acts like a cosmic magnifying glass. As light from a distant object, perhaps another galaxy or a quasar, travels towards us, It passes through the warped space-time around the foreground cluster. The light rays are bent, distorted, and magnified, creating multiple images or elongated arcs of the background object. These celestial mirages not only offer us stunning visual spectacles, but also provide invaluable insights into the distribution of dark matter, the unseen scaffolding that holds these colossal structures together. By observing how light is bent, scientists can map the invisible gravitational influence of dark matter, revealing its hidden presence. Another profound consequence of space-time curvature is time dilation. According to general relativity, time itself is not absolute but relative, flowing differently depending on the gravitational field and relative velocity. In regions of stronger gravity, time slows down. While imperceptible in our daily lives on Earth, this effect is crucial for technologies like the Global Positioning System, GPS. Satellites orbiting Earth experience slightly weaker gravity and higher velocities than we do on the ground, causing their clocks to run fractionally faster. Without accounting for these relativistic effects, GPS systems would quickly accumulate errors, rendering them inaccurate. This tiny, constant adjustment reminds us that our universe is far more intricate and dynamic than our everyday perceptions suggest. The most extreme manifestation of spacetime's curvature, however, is found in the enigmatic realm of black holes. These cosmic behemoths are born from the catastrophic collapse of massive stars, whose cores, after exhausting their nuclear fuel, can no longer withstand the crushing force of their own gravity. The stellar remnant implodes, compressing an immense amount of matter into an infinitesimally small point called a singularity. Around this singularity forms a boundary known as the event horizon, a point of no return. Beyond the event horizon, the space-time curvature is so extreme that nothing, not even light, can escape its gravitational embrace. From an outside observer's perspective, anything falling into a black hole appears to slow down, dim, and eventually fade away, frozen in time at the event horizon. Black holes come in various sizes. Stellar mass black holes, typically a few to tens of times the mass of our Sun, are the remnants of individual massive stars, but the universe also hosts supermassive black holes. Gargantuan entities millions to billions of times the Sun's mass, residing at the hearts of most, if not all, large galaxies, including our own Milky Way. Our galaxy's central supermassive black hole, Sagittarius A star, is about 4 million times the mass of the Sun. These colossal anchors are believed to play a crucial role in galaxy formation and evolution, influencing the birth and motion of stars in their vicinity, though the precise nature of this co-evolution remains an active area of research. While often depicted as cosmic vacuum cleaners, black holes are not indiscriminate devourers. They only pull in matter that ventures too close. Outside the event horizon, their gravitational influence is similar to that of any other object of comparable mass. The very processes that create black holes, along with the violent mergers of these space-time monsters or the collision of incredibly dense neutron stars, send ripples through the fabric of space-time itself. These ripples are called gravitational waves. For decades, these elusive waves were predicted by Einstein's theory, but remained undetected due to their incredibly subtle nature. It was not until 2015 that the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting gravitational waves for the first time. originating from the merger of two stellar mass black holes over 1 billion light-years away. This monumental discovery opened a completely new window onto the universe, allowing us to quote 28 the most cataclysmic events in the cosmos, rather than just seeing them with light. Gravitational wave astronomy is still in its infancy, but it promises to revolutionize our understanding of black holes, neutron stars, supernova, and even the very early universe. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves pass through matter unimpeded, carrying pristine information from the heart of cosmic violence. We are now beginning to build a multi-messenger astronomy, combining observations from electromagnetic waves, light, neutrinos, and gravitational waves to paint a more complete picture of the universe's most energetic phenomena. As we ponder these grand cosmic scales and the intricate dance of space-time, it is also worth acknowledging the universe's equally profound mysteries at its smallest scales, the realm of quantum mechanics. Here, the rules that govern the everyday world, the predictable paths of planets, the steady flow of time, break down. Particles can exist in multiple states simultaneously, communicate instantaneously across vast distances, and appear and disappear from existence. The universe, it seems, speaks two distinct languages: the elegant curvature of space-time for the very large and the probabilistic, often counterintuitive, language of quantum mechanics for the very small. Reconciling these two fundamental pillars of modern physics into a single, unified theory of quantum gravity remains one of the greatest challenges in science. It is a frontier where our understanding is still nascent, where the deepest secrets of reality may yet be hidden. This continuous interplay of forces, from the quantum foam to the cosmic web, speaks to a universe of constant evolution and recycling. From the fiery crucible of the Big Bang, through the birth of the first stars, the synthesis of elements, the formation of galaxies, and the emergence of planetary systems, the cosmos is a dynamic, ever-changing entity. Stars live and die, scattering their enriched elements back into space to form new generations of stars and planets. Galaxies collide and merge, reshaping themselves over billions of years. Matter and energy are perpetually transformed, moving through grand cosmic cycles that underpin all existence. Our own solar system, our Earth, and indeed all life within it, are but fleeting expressions of this majestic, ongoing cosmic ballet. Despite the vast knowledge we have accumulated, the universe remains an infinite wellspring of mystery. Dark matter and dark energy, which together constitute about 95% of the universe's mass energy content, continue to elude direct detection and definitive explanation. Their existence is inferred from their gravitational effects, but their true nature is unknown, representing perhaps the most significant gaps in our current understanding. The origins of consciousness, the precise mechanisms that sparked life from non-living matter, and the ultimate fate of the universe itself, these are but few of the profound questions that continue to beckon us into the unknown. As we conclude this chapter, we are reminded that our journey of discovery is eternal. Each answer we find illuminates a path to new questions, deepening our appreciation for the universe's complexity and beauty. We invite you to hold this sense of wonder, this peaceful curiosity as you allow your thoughts to drift. The cosmos, in all its grandeur and mystery, is a canvas upon which our understanding is continuously painted. a testament to the unending quest for knowledge and the boundless capacity of the human spirit to explore, to question, and to find stillness amidst the infinite.